All right, a great pleasure to have Mark Sellke from Stanford. Mark, take it away.
Okay, so thanks very much for the invitation. So I'll talk about multiplayer bandits without communication. I'll mention two works I was involved in, one of which was with Sebastien and Thomas, the other of which was with Allen. But I'll take a little bit to get there. I'll start by first setting up what is multiplayer bandits, and then I'll really talk for a bit about communication and why it is an important keep careful track of when studying this problem. And then in the second half, I'll say a bit about how you can get square root T regret and even some gap-dependent regret bounds for this problem in a pretty strong sense with kind of no communication, no collisions. Okay, so let's start. So we all know the standard stochastic bandit problem. We have some finite set of actions. Each one has some reward probability. We don't know what the reward probabilities are, and we want to get as much reward as possible over time. And usually what we keep track of is the regret. So this is the difference between the total reward from the best arm and the total reward that we end up collecting ourselves. And there's kind of two different types of regret bounds that one kind of typically looks at. So the first main one that you'd look at is getting square root T regret. So here you don't care what the probability of reward for each arm is at all. In this bound, you just want square root T no matter what. And then maybe the second thing you'd look at is getting a gap dependent bound. So you want your regret to scale like log T over delta, where delta is the gap between the best and second best arm. Okay, so these are kind of the things we'll be interested in looking at in a multiplayer setting. How is multiplayers going to work? Well, we're going to have multiple players. I'll call them X and Y. You can often just think about two players, in fact. And the interesting thing is that the players are trying not to collide on the same arm. So if you and I are playing and we pick the same arm at the same time, that's a collision. That's very bad. Neither of us gets a reward. And I'll say a bit more about like there's some choice in deciding exactly how bad it is, but somehow it's a bad thing. And we're going to be in a full cooperation setting. So there's no game theory, there's no incentives, there's no Nash equilibrium. And so we have a very simple to state benchmark. We're just trying to collect as much reward as possible. So the kind of optimum thing to do would be one of us just goes on the best arm every time, the other of us gets on the second best arm every time. And so that's kind of our regret benchmark. So this model was proposed for wireless radio communications. So it is maybe I want to pick a good frequency, you want to pick a good frequency, but we don't want to interfere with each other. And if we can kind of work together throughout this process, then this is just a semi-bandit problem. So instead of picking one arm every time step, we pick maybe two arms every time step. We try to get the best pair of arms. This is, there's online shortest path is some variation of this. But we're going to be aiming for a distributed algorithm where we cannot communicate with each other. So somehow we have to come up with some protocol beforehand so that one of us ends up on the top arm, the other one of us ends up on the second best arm, and we somehow don't synchronize or talk to each other at all in doing this. Okay. Now there's a lot of possibilities for algorithms. In a sense, the central difficulty is that it's hard to break ties. So we could say that I'm going to try to get the second best arm, you're going to try to get the best arm, but okay, maybe they're very close together. How can we, we have noisy measurements. We don't see exactly the same feedback. Like, how do we figure this out? And if we can detect collisions, this helps a lot. That's kind of the first thing you might think of trying to do here. Because if I can tell when we collide, then we can communicate with each other. So this was observed, for instance, in this paper by Alatur, Levy, and Krauss. So they showed this pretty simple algorithm to get T to the 2/3 regret if you can detect collisions. So here's what you're going to do. You're going to break your T time steps into blocks of length cube root of T. Within each block, everyone's going to do the same thing until the next block. But in between blocks, we're going to spend just a little bit of time, like log t time, synchronizing with each other. We'll just communicate a little bit using these collisions as ways to send bits, and we'll sync up all our information. And this just reduces to a semi-bandit game, and you get t to the 2/3 regret by just doing this reduction. Okay, but this isn't really a distributed algorithm. I mean, somehow the communication via collisions is maybe too powerful. And actually, yeah. Is there a question?
Out of curiosity, because I lost it, at the end of the day, what is not communication, but we have detectable collisions? Well, how we learn that we have detectable collisions since we do not communicate?
Sorry, can you repeat that?
You say that we do not communicate, but on the other hand, we have the ability to detect collisions. So who tells us that? The system? How we learn that?
Right. So I guess the question is about the difference between, like, what do I mean when I say there's no communication?
Yes.
Yeah, right, exactly. So kind of, if communication is really for free, I'm kind of saying communication isn't really for free, but yes, totally, this is basically communication. It's just a hack to get around it. So what I'm trying to go through is kind of how we can eventually get to a problem setup where there's really no communication. So I'm kind of treating this as a bad problem setup, because you can embed communication inside it. So I hope that.
So I think it was just a basic question about like the feedback model. And just to be clear, the feedback model is, everyone plays their arms and gets sees their own rewards and sees a bit that says whether or not there was a collision. That's what the detectable collision model is, right?
Yeah, exactly.
Yeah.
So if I collide, then I see not only that I received 0 reward, I get told, you got 0 reward because there was a collision. Yeah. Kind of very explicit.
Thanks.
Yeah, thanks. I should have been more clear about that. Yeah, so not surprisingly, if you get this explicit feedback about collisions, you can do a lot. In fact, you can even get square T regret with adversarial rewards by doing a more complicated version of this idea. Okay, so the takeaway I want to kind of get from this is that we should set up the problem better to not allow communication. So let's try to do that. So here's my setup. I'm going to have my unknown reward probability vector. I'm going to have independent Bernoulli reward variables for any arm and every time, even every player. And at any time, if a player X chooses an arm ITX, they receive a reward, which is given by the underlying Bernoulli random variable times 0 if there was a collision. So if it's times 0 if he collided with someone else. So that's the reward you get, and you do not get to observe whether a collision occurs. And like I mentioned before, the regret is kind of the difference between the total reward accumulated by all the players together and the sum of the best M arms. Okay. Maybe surprisingly, there's still a choice to be made about how to set up the problem, because I haven't told you what feedback is actually received. So here are two very natural models. The collisions can either be weakly detectable or undetectable. So if the collisions are weakly detectable, I'm going to say that means we actually observe the reward that we receive. So if I collide, I'm going to receive 0 reward, and I'm going to be told that I got 0 reward. So the collision affects my feedback. So I don't get told why I got 0 reward. I don't get told the collision happened, but I see the 0 reward. But I could also have undetectable collisions. Maybe the collision messes something up further down in the pipeline, and I don't actually see it. I just see the reward I would have gotten otherwise. Okay. So we have these two models. Are they equivalent? Is one harder than the other? How do they compare to maybe a less clean collision model where the behavior of collisions is more arbitrary? Does either one of them lead me to have to think about decentralized algorithms? So, a lot of questions. Here are some answers that I'll explain in more detail in the rest of the talk. So first off, if you want to get square root T regret, you can still do it in either case. But you can get much better gap-dependent guarantees if you have weak detectability. So if your reward is 0 when you collide and you get to see that your reward is 0, then you can get 1 over the gap up to log T factors and stuff. But if collisions are totally undetectable, they don't affect your feedback at all, then the gap dependence behavior gets a lot more complicated. And there's a whole range of Pareto optima gap dependence curves ranging between square root T and 1 over the gap squared.
Mark, let me ask you again. So what does it mean now, the feedback that you get? I mean, you say collisions affect the rewards. Do the players see the rewards or no?
Right. So in the first model, which is labeled A here, your feedback is exactly the reward that you receive. So if there's a collision, then you observe the 0. In the second one that's labeled, in the second one, you observe the Bernoulli variable that corresponds to the reward you would get, assuming there's no collision. So if there's a collision, then you don't observe it. You think you got a reward, but you actually didn't.
Okay.
Yeah. So like one reason this is something that's good to think about is that here there's really no way to communicate at all. Like your feedback is totally independent of what anyone else does. In the first case, in the weakly detectable case, there's still some potential to transfer information between players. Yeah. Does that answer your question?
Yeah, it's fine.
Awesome. Yeah, thanks. Okay, so I'll keep going. So in this case of undetectable collisions, the gap dependence gets more complicated, and the optimal guarantees are actually.
Sorry.
Yeah.
Sorry, quick question while we're playing with the model. We considered the case where if there's a collision, the adversary is allowed to know you picked it and give you whatever reward it wants to mess up your algorithm.
Yeah.
But you have considered that case.
Yeah. So I'll say in a moment. The undetectable case is the hardest case, and it's solved by algorithms that just never collide at all. So like the algorithms I'll actually talk about will just have no collisions at all. So they'll also solve the case you're proposing.
Great, thank you.
Yeah. So that's exactly like the kind of thing that you might have in mind. You can have a malicious adversary that does something really weird when there's a collision. And if you have an algorithm that never collides at all, then you solve that case also. But it's maybe surprising that just saying that collisions don't affect your feedback is just as hard in terms of the optimal regret bounds. Yeah, so that's kind of what I was getting to. So if you just care about minimax regret, then in any feedback model, you get square root T. But if you care about gap dependence, then weakly detectable is easiest. So when you see the actual reward you got, the gap dependence is the same as in the standard one-player bandit. If you, on the other hand, the worst case for gap dependence is obtained by collision-free algorithms, and it also is kind of witnessed by the undetectable collision case. Yeah, and the nice thing about collision-free again is that it solves any case of the problem, even if there's an adversary. Any more questions about this stuff? This is a good part to ask questions about, probably. Okay, great. Yeah, keep asking questions, but I'll keep going if there aren't any. So let me first spend just a little bit saying what happens when there are weakly detectable collisions. So when you observe 0 when there's a collision. So this was an idea from this nice paper of Huang, Combs, and Trin, and there was a later work with some similar conclusions as well. So the first step is that the players somehow agree on a decent arm. So maybe it's not so easy to agree on the best arm, but somehow they manage to synchronize on a decent arm that's, within a constant factor of the best reward probability. And then they're going to use this arm as a gadget for communication. So they're again going to take even this weaker amount of detectability and turn it into communication. And the way it's going to work is kind of, if I want to communicate, I'll play this special arm for a while. And I'll play it for long enough so that if I receive no reward while I was playing it, I know someone else was also playing it. Like in this first phase, I have some decent estimate of its reward probability PJ. I know that if I play it for a lot more than 1/PJ time, it should give me a reward. So if it doesn't give me a reward, I know someone else is kind of on the other side of the wall trying to talk to me also. So if I don't see any reward, then we try to talk to each other, and we just do this by exchanging bits using, again, just like blocks of time when there's no reward on this arm. So somehow you can implement this. And the nice thing is that there's some cancellation. So because the arm is close to the best arm, the regret from doing this communication procedure is not too high if the reward probability PJ is small. So there's kind of this cancellation. So even if it takes a long time to send a bit, like 1/PJ time, the regret of this communication is just like basically 1 per bit we send. So as a result, we kind of can build this communication protocol that works very well regret-wise, and we can just do whatever. So I think this is very nice. In fact, you don't even need to have like 0 reward as long as the mean reward is a little bit lower than the non-collision reward. Then you can detect this kind of thing. But it's still communication. So what I'll focus on for the second half is algorithms that really have no communication at all. And as I've been saying, this means that there's not only no communication, but there's no collisions at all, so they work in any model. So the main result on Minimax Regret is with Sebastien and Thomas. And what we showed is that you can get regret square root t log t times some polyfactors in the number of actions. And the probability that there's ever a collision is something like O of t to the -2. You can make that -2, -100, it's all fine. In fact, the log is real. So even with full feedback, the log t is really there, which is a little surprising because it's not true in the single player case. And here there's a specific definition of full feedback I'm using. I'm saying all the rewards are independent. So even if you and I both try the same arm at the same time, in full feedback, we'll see different things. Like the arm will give rewards independently to different players. That's kind of a nice full feedback model here because it prevents any shared information. So to see how this works, let me first explain kind of a topological obstruction in the case of 2 players and 3 arms where we can draw a picture. So I'm going to work in the case of 3 arms, and I'm going to work in the plane capital P where the total reward probability is a constant. And I'm going to work in a full feedback loop. And because we're assuming some kind of undetectability or no collisions, the actions of one player don't affect the feedback of the other players at all. So if there's just 2 players, basically I just have pre-specified functions. So at time 10, I will have pre-specified my function, which tells me, if I saw this amount of average reward from each of the arms, so I have these empirical estimates for each arm's reward probability, here's what I'm going to do. I'm just going to have this function ready in advance. the other player is going to have this function ready in advance, and we need to design these functions so that there aren't going to be collisions. And if you try to do this naively, there's kind of an issue. So basically, you can think that the two players have empirical estimates of the true reward vector p, and they're close to each other, but there's some noise of order 1 over square root t. And what you would try to do is always play the top 2 actions. So in this, this triangle is kind of the state space of possible probability vectors. So there's a corner for 1 best, 2 best, 3 best, and so on. So these green regions are kind of corresponding to a greedy strategy where we're always playing the top 2 actions according to our estimates. But you get this topological obstruction if you go in a circle. Kind of, you can't transition between 1, 3 and 3, 1 without causing some collisions to happen. Because if you just have a line separating 1, 3 and 3, 1, that's saying that like if my estimate is in the 1, 3 region and your estimate is in the 3, 1 region, then we're going to play the same action. We're going to collide. So here these pairs are kind of like my action, your action. So if I'm in 1, 3 and you're in 1, 2, then that's fine. There's no collision. But if I'm in 1, 3 and you're in 3, 1, then maybe we both play action 1. Does the picture make sense, or should I say more about what this means?
Sorry, what is the cumulative loss from colliding sometimes?
So we're just going to try to not collide at all, basically. So you can just
I
think
guess to understand your abstraction here, I mean, the point you're trying to make, I mean, like, yeah, sometimes our estimates are going to be off and we're going to disagree, but eventually, hopefully, we're going to resolve. I mean, how, like, if you try to aggregate the loss coming from this, you know, large deviation bounds, but like, how bad is it? I mean, is it root t or is it like it can kill you? I mean, yeah.
So you're thinking of collisions are like really undetectable.
No, I'm not talking about collisions. I'm talking about estimates for the rewards of the arms. So yeah, I understand that the p hats are different from the real p's. And maybe we have, I think it's 1, 3, you think, I mean, I think the top is 1, you think the top is 3, and you know, like, but okay, like say when this happens, like in the rounds, this happens, we collide. You know, okay, so we both receive further information, so which makes our p hat better. And you know, are we going to resolve? Are we going to get out of this problem or not? I mean, that's I guess the question. Or like if I were to add a little bit exploration around, you know, whatever, like my uncertainty or something, collect more data, maybe, you know, and so on and so forth, mix it up. Like, can I get out of this rabbit hole, or is it a problem? Like,
so I think if you're really in this undetectable model, like it's possible for it to be okay, I think. But like in most cases, when you're thinking about this problem, like, you know, there's some, you know, like if your feedback gets corrupted when you collide, then you just can't really start analyzing what happens with a small number of collisions. Like you're just going to be way off forever in the future.
oh, I see. Yeah, I was talking about the undetectable. Yeah, that's right. Yeah.
I think with undetectable, it may be kind of okay to kind of close your eyes and just do something simple here. Yeah. But I think it's really a better guarantee to try to avoid collisions entirely.
Yeah. Oh, yeah, thank you.
So here's what you can do to avoid collisions. So this is an idea of Sebastien Bubeck. What you do is you break this topological obstruction by putting some padding here. So that's shown in orange. So we're going to intentionally play this bad action 2 when our estimates of p are in this padding there. So this is going to have a small chance of making us, I mean, it's going to sometimes make us make bad decisions, but it's going to prevent collisions because we just have to make the padding wide enough so that we're never on opposite sides of the padding. Okay, and if you kind of put the orange padding layer in a random location, like you give it a random angle, then on average, you're gonna hurt any given problem instance a small amount. You're kind of spreading out the extra regret. And outside the padding, you can just be greedy, so you can get square root t regret. And another thing is that everything, like these pictures, you can kind of think of things as full feedback, but things become a lot harder if you have bandit feedback. So like it turns out you can turn this picture into an algorithm, but yeah, if you come up with some other way to do this, it might be hard to turn it into a bandit feedback algorithm. I won't say too much about that part. So kind of the first thing is that, well, how does this picture work in higher dimensions? You know, if I have a k-dimensional simplex or something, what are we going to do? So we came up with a more general partition that extends to fully general numbers of players and number of arms. Here's what it looks like in the same two-player three-action case. It's kind of a tree. So you can think that the orange region is the root of some tree, and kind of the purple and the light green are its children, and the dark green are the children of the purple. And these regions are formed by arm inequalities added in order. So at the root, the label is kind of just 1, 2, 3 with no inequalities. So we have our three actions, and we haven't made any decisions about which ones are better than which others. But in, for example, these light green regions, we have some inequalities. Like in the bottom one, the inequality is that 2 and 3 are both bigger than 1. So that's telling me that actions 2 and 3 are better than action 1. And once we add more inequalities, we're also going to keep track of the order in which we added them. So in kind of more generality for a bigger picture, you could have this thing with 3 inequalities I have on the bottom here. 1, 3, 5 is bigger than 4, 8 is bigger than 2, 6 is bigger than 7, 9, 10. And we're keeping track of the order we add these inequalities, which allows us to get some tree structure. So the idea is that these orange and also purple regions are serving a similar role of padding to kind of separate out the main part of the diagram, which are these green regions. And the orange and purple are in random locations. So there's kind of a general nice way to think about this less pictorially. First off, you never compute with the full tree. So there's a huge number of regions, but you can just take in an empirical arm estimate, an empirical estimate of the probability vector, and output what the partition tells you to do efficiently. And the way that this works is that you start with just all the arms and you don't know anything about their relative order. And you repeatedly try to kind of add new inequalities to separate arms that might be in the top M. And once the top M and the bottom K minus M are determined, then you stop adding inequalities. You've kind of found a leaf in the partition tree. So here we start with all 10 actions. We're trying to find the top 5. So we first add this inequality that breaks off the best 7 versus the bottom 3. So now we know that the bottom 3 are not relevant anymore, but all of the top 7 are still relevant. Then we break off the top 3. So those guys are no longer relevant because they're definitely in the top 5 that we're aiming for. But there's this middle group of 4 where we need to pick out the best 2. So once we do that, then we're done. We've found a leaf in our partition tree, and we'll have some pre-computed label that tells each player what to do. And we'll decide whether to add these inequalities based on some random thresholds we've picked before. So there's a lot of shared randomness used here just beforehand to compute, to prescribe how to compute these partition trees. And the padding layer comes when you're very close to adding the inequality or not. Okay. Now in this construction, if we turn to looking at gap-dependent regret, which is the last thing I'm hoping to talk about, the square root t additional regret from the random padding applies for all the gaps. So you really get square root t for anything. This is not so great. So if we want to improve things for large gaps, we should kind of push the padding away. And here's how we did this. So this is with Allen. We designated the problem instances with a large gap, larger than some threshold delta 1, as safe zones. So they kind of don't have any padding. So these are these blue triangular regions. These turn out to be the regions with very large gaps in this case. And we do the same padding tree construction, but if the padding tries to enter these safe zones, it just kind of doesn't enter them. It kind of bounces off the side is what the picture ends up looking like. So if you have a problem instance with a large gap bigger than this delta 1, so you're kind of well inside this safe zone, then before too long, everyone's estimates will be well inside the safe zone, no padding will get involved, you have zero regret from that point on. So you're doing much better for problem instances with a high gap. On the other hand, this has a cost. It makes things worse when you don't have such a large gap. And the reason is that the padding location becomes less random. So before, these padding regions were just kind of totally random. They were kind of width 1 over square root t. They were totally random. So you had like a 1 over square root t probability to run into them, which adds up to root t regret. But now the padding, the safe regions kind of restrict the possible locations of the padding regions by a factor of 1 over this delta 1. So the result is you get a better performance for large gaps, but a worse performance for small gaps. There's this trade-off here. And this turns out to lead to the best possible algorithms for the problem if there's undetectable collisions. And in fact, it still works in a collision-free way. So more generally, what you're going to do is you're going to fix a sequence of different gap sizes. This is kind of a schedule along which you're going to use this kind of algorithm. And so after you get to time bigger than delta j to the minus 2, you switch to that scale. And the result of this is a regret guarantee of at most 1 over delta I times delta I plus 1 for gaps that are bigger than delta I. And these are Pareto optimal in the sense that these are the best trade-off curves up to poly k log t factors. So if you want to get better than one of these curves, you have to be worse somewhere else. Your regret has to suffer somewhere else if you're better at some point. So this has a lot of nice consequences and examples. So one example is if your gap size schedule delta i's are going kind of slowly, like by a constant factor every time, then basically the regret is going to be 1 over the square of your gap. On the other hand, if you just have like delta 1 equals 1 and delta 2 equals t to the minus 1/2, so you have as little going on as possible, then you'll recover the square root t regret. And so you can kind of say in several senses that square root t is kind of optimal and sort of a stable optimum. So if your regret is less than t to the 0.51, then you cannot do better than square root t regret for gaps that are smaller than t to the minus 0.01. So there's some senses in which you can say that, you know, if your regret was good, then it has to suffer somewhere else. Let me just say a little bit briefly about how you prove this. The idea is some kind of topological obstruction again. So you're going to put square root t points kind of uniformly around a circle and think of adjacent pairs of points as plausible pairs of like my estimate comma your estimate. And there's some topological obstruction saying that somewhere around this circle there has to be a fail. Either there's a collision or we play the bottom 2 out of 3 actions. And by some kind of pigeonhole argument, this says that you have a lot of fails at some gap level, and this leads to some amount of regret. Now, this is just saying there exists some gap with a lot of regret. So how do you get this lower bound with many gap sizes? Well, the idea is to apply this lower bound repeatedly. So maybe this lower bound, so there's this purple curve here with regret square root t over delta. This lower bound will tell me that my regret curve has some point on this purple. And once I have that, I can say, okay, I'm gonna look at only the first delta j to the -2 time steps. So now this delta j point that I found, the red point on the curve, doesn't count as a large gap anymore. It's just 1 over square root t. So now I can kind of apply the lower bound again on this smaller time scale and get another lower bound point. And if you iterate this kind of lower bound procedure, you end up with the same Pareto optimum trade-off I showed before. Okay, let me just wrap up. So maybe the main takeaway of what I've said at a high level is that if you're thinking about multiplayer bandits, the details of how you set up and think about collisions really matter a lot. So if collisions are weakly detectable, if you get to see the 0 reward, then you can still get the kind of best case regret. You can get both square root t and you can get log t over delta. But if you can't detect collisions, then the regret gets much larger, at least for large gaps. And these trade-offs are achieved with no collisions at all. So this is kind of something that you can do in any collision model. There are a lot of directions that aren't so well understood. Adversarial rewards are still posing some issues. You can make up all kinds of more richer feedback structures, and you can think about what this might have to say for RL. Here's a picture of the final algorithm and the Pareto optimal regret curves I discussed at the end. Thanks very much, and let me know if you have any final questions.
Thank you very much, Mark. This was fun, very interesting. Any questions in the room? So Dylan, are you monitoring the chat?
Yeah. There's no questions in the chat right now. I mean, an obvious one maybe is like, do you want to say something a little bit about the non-stochastic rewards, or what the challenges are there?
Yeah, I think it's just quite a bit harder. Like,
I mean,
like,
intuitively.
So if collisions are detectable, you can, or like strongly detectable, like you're told whether you collide, you can get this square root t algorithm. Like, yeah, I just don't know that much you can do. I think it's just very open. So we had some algorithm where you run learners that have like low swap regret with kind of very different learning rates, and you can do something. So kind of if there's m players, then you get regret like t to the 1 minus 1 over 2m by kind of black box running a bunch of learners with low swap regret at different scales. But an exponent of 1 minus 1 over 2m is pretty bad.
Interesting. So even like t to the 2/3 or something is open.
Yeah, I think that's right. So I guess I've like, people have like, there have been some suggestions to try to imitate the algorithms I was discussing, but using some kind of like log barrier mirror descent instead. Like, it seems like this might be something that one can do, but it seems much more complicated. I'm not sure what the, like, I think there's nothing like published on this. I'm not sure if the idea has like gotten somewhere or what.
Cool, thanks.
Do you have any thoughts on more general feedback structures? Like, for instance, maybe there's some subset of pairs of arms such that if the agents take those pairs, they don't see anything, or more general, basically generalizations of collisions.
Yeah, yeah. I think there's a lot of open directions here. And I think that's a very interesting one. That's kind of the sort of thing I was indicating when I wrote network structure on this slide, actually. Just, yeah. Yeah. You can also think, arms behave differently for different players. Maybe there's some kind of coordination game aspect. I think there are a lot of directions here.
All right, so it's getting late. Let's take further questions offline, and thank you again for the stuff. Thank you very much.
Yeah, thanks a lot for having me.
All right, so see you tomorrow. And also, there is a